starting with SN2 now. Do you know anything about SN2 reaction? Yes, Rufia.
Yes.
Yes, I'm waiting for your answer.
SN2 is also a nucleophilic substitution reaction where
Yes.
bond is broken
Yes.
and another is formed, right?
And okay, fine. So SN2 reaction is substitution nucleophilic bimolecule.
Okay, yes.
This 2 indicates bimolecular, 2 steps, but this reaction takes place in only 1 step. Fine.
Yes.
So basically in a nucleophilic substitution reaction, the existing nucleophile is replaced by another nucleophile, right?
Yes,
So
yes.
in SN2, a transition state is formed. Do you know what is transition state?
Yes.
We'll just take an example. So suppose we have CHCl. And this nucleophile is OH minus hydroxide ion. So this is your substrate and this one is your nucleophile.
Yes.
Okay. Now this hydroxide ion can attack through this side also, as well as through this side also, front side also and back side also. Fine. So in this, the bond breaking and bond formation, it takes place simultaneously. That means in a single step, both the processes go on. So we can write like this, that the bond between CCl has started breaking and the bond between carbon and OH has started forming. So we have shown it with a dotted line because bond formation and bond breaking is going on simultaneously. And then we can represent like this 3 hydrogen atoms. So can you see that in this state, the carbon atom is bonded to 5 other groups, right?
Yes.
So this is your transition state, which is having higher energy, which is unstable, and this will get decomposed to form our product.
Okay.
Okay, so now can you see that earlier chlorine was present on this side and now this nucleophile has attacked from back side. So now it has been attached on this side. So can we say that there is an inversion of configuration? The existing configuration has reversed, right? Because the nucleophile has joined from the back side. So you should remember in SN2, inversion of configuration takes place. Like you can imagine umbrella. What happens when a strong wind flows? The umbrella turns upside, right?
Yes.
The same here. So if this was attached earlier here, so it will be attached this side now. And the nucleophile will go. The previous nucleophile Cl minus will go. Understood?
Yes, ma'am. Yes.
So in SN1, we were talking about the stability of carbocation, but in SN2, we talk about steric hindrance. Do you understand steric hindrance?
No, I don't.
Okay, I'll explain. See, in this, the nucleophile has to approach this carbon, right? The nucleophile has to approach this carbon. So if the groups attached to carbon are already bigger in size, they are bulky groups. So will it be easy for the incoming nucleophile to approach this carbon?
Yes.
Listen it again. I'm saying that if these groups, like now they are written as H, but suppose if there are bigger groups attached, bulky groups are attached to the carbon, and you know that nucleophile approaches from this side. So will it be easy for the nucleophile to approach this carbon if bulky groups are present? I'll show
Yes.
you. See, suppose carbon is there and 3 hydrogens are there. So there is a way for the nucleophile to come. But if around carbon, bigger groups are present. So will it be easy for the nucleophile to approach?
Oh,
Will it be easy now?
yes, it will be.
No, it won't be easy because you can see that these groups will hinder the approach. They'll stop the approach of nucleophile.
Okay, 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 I understood.
That's what I'm saying. Like whenever the group is small, the nucleophile can easily approach the carbon. But whenever the groups are bulky, it's difficult
Okay,
for the nucleophile to approach. That is steric hindrance, the
oh,
obstruction. Okay, in the path
yes,
of. Now understood?
yes, understood, understood.
Okay. Now imagine primary, secondary, and tertiary halides. And then tell me which one will be having the least steric hindrance, primary, secondary, or tertiary? Yes.
Yes, ma'am.
Now tell me which one will be having the least steric hindrance, primary, secondary, or tertiary?
It's tertiary.
Tertiary. Okay. Do you have a notebook with you?
For writing, yes, I'm writing.
Yes. Okay. So just draw the structure of tertiary chloride.
Okay. Yes, I wrote, ma'am.
How did you write the structure?
Um, Carbon in the middle, and then it has three bonds, three CH, three bonds, and then one Cl bond.
Okay, correct. Now you can see that 3 CH3 groups are present, right?
Yes.
Now draw the structure of isopropyl chloride.
Okay. Chloride, right?
Yes, isopropyl chloride.
Two CH3 bond and one Cl.
Yes.
Okay.
Okay, now draw ethyl chloride.
Ethyl.
Yes, ethyl chloride. So you have CH3, one is methyl chloride, So methyl chloride will be having 3 CH3 groups, right? CH
Yes.
bonds. And there will be one halogen. Now, if we
Yes.
talk about ethyl chloride, it will be having 2 CH bonds, right?
Yes, and one Cl.
One Cl bond and one CH3 group. That means this carbon and along with it, 3 hydrogen are attached, right?
Yes.
Now we are talking about secondary. So it's having 3 Cl and then there is one hydrogen and then 2 CH3 groups. Can you see the screen?
Yes, ma'am. No, I can't.
Now is it okay?
Yes.
So we have another CH3 group. So this carbon is having 3 hydrogen attached to it, right? And then we have tertiary one. So there is one Cl and there are 3 carbons attached to this carbon. And there are further 3 hydrogens attached to every carbon, right?
Yes.
This is the actual structure. Now this is your methyl chloride. And now you can see that this is Cl and Cl is bonded to this carbon and this carbon is further attached to only one carbon. So this is primary. And here you can see that Cl is attached to this carbon. And this carbon is further attached to 2 carbon atoms, right?
Fine.
So
No,
it is secondary.
secondary.
Yes. And this carbon is further attached to 3 carbon atoms, right? So it is
Yes.
tertiary.
Tertiary.
Now, can you see that in which halide what can I say, that smaller groups are present?
Yes.
The size of group is small. You can see in hydrogen, it is small.
Yes.
The nucleophile can easily approach, right?
Yes, ma'am.
In primary, this is present and these 2 groups. Here also, it is somewhat easy for the nucleophile to approach. Now, if we talk about this group and this bulky group, here it is a little difficult for the nucleophile to approach because there are 2 bulky groups present, right?
Yes.
But in the tertiary, if we see, we have 3 CH3 groups. So it becomes really difficult for the alkyl halides, for the nucleophile to approach the alkyl halide. Understood?
Yes.
So can we write the order of SN2 reaction? So order of reactivity for SN2 is?
Tertiary was.
No, it will be methyl halide.
Okay. Of that way. Methyl.
Because it is having least steric hindrance, least crowding is there. Then
Yes.
we'll have primary, then we'll have secondary, then we'll have tertiary. Fine.
Yes.
So you should remember that methyl halides react rapidly in SN2 reaction because only 3 hydrogen atoms are present, which are smaller in size. And these tertiary halides, they are the least reactive. They are least reactive and methyl halides are most reactive.
Yes, ma'am.
Because of the size of the groups. And you should remember that bulky groups means the groups which are bigger in size. So bulky groups hinder the approach of nucleophiles. So you should remember this reason. So in SN1 reaction, we talk about stability of carbocation, whereas in SN2, we see steric hindrance of the groups. That how easily our nucleophile is able to approach the carbon. Have you understood? Rufia, have you understood?
Yes, ma'am.
Okay, noted.
No, ma'am, just 1 minute.
Okay. Any doubts in this?
No, ma'am.
Okay. So this was all about the first type of chemical reaction, which is shown by alkyl halides. Now the next one is, do you remember the next one?
The next one.
First was nucleophilic substitution, right?
Yes.
Next is elimination reaction. Third is reaction with metals. Do you remember?
Yes. Yes. Yes.
So next we'll discuss elimination reaction.
Now, can you just give me 1 minute?
Yes, sure.
Yes, ma'am.
Shall we start now? Okay, tell me about reaction, elimination reaction. Rufia, do you remember elimination reaction?
Yes. Yes.
What is that?
We did. I know. I know. I know. It's a type. No, 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 no. It's a chemical reaction where several atoms are or pairs or groups are removed from a molecule.
What that means? Yes, a molecule is eliminated.
Yes. Yes.
So in this elimination reaction, we have a haloalkane. Haloalkane is your alkyl halide, right?
Yes.
And it should have a beta hydrogen atom. So we should have an haloalkane with beta hydrogen. Do you remember alpha, beta, all these
Yes.
numbering?
Yes. I know.
Okay, suppose we have this carbon. So the carbon to which the functional group is attached or the halogen is attached, that is called as alpha, and the next carbon is beta. And the hydrogen attached to beta carbon is called as beta hydrogen. So we should have an haloalkane with beta hydrogen atom, right? And then this haloalkane with beta hydrogen atom is heated with alcoholic solution of potassium hydroxide. Alcoholic solution of potassium hydroxide. And then we'll observe that there is an elimination of hydrogen atom from beta carbon and halogen atom will get eliminated from alpha carbon. Fine.
Yes.
So you have to remember that from beta carbon, hydrogen atom will get eliminated, and from alpha carbon atom, halogen will get eliminated. So whenever we heat a haloalkane with alcoholic solution of potassium hydroxide, this elimination reaction will take place and it will form an alkene. Forms alkene. Okay. So now you can see that in this, the beta hydrogen is eliminated. That's why it is also called as beta elimination reaction.
Okay.
Understood?
Yes, ma'am.
Now suppose here the product is alkene. Now in some examples, there will be a possibility of forming more than one alkene. More than one alkene will be formed in some questions. So then how will you decide that which one will be the major product? For that, you must have studied Sezef rule. Do you remember this rule?
No.
Okay, so whenever there's a possibility of formation of more than one alkene, you will decide the major product by this rule. So this rule states that in dehydrohalogenation reaction, So what is dehydrohalogenation reaction? Yes, what do you understand by dehydrohalogenation?
Um,
Okay, I'll
it,
explain.
uh,
First note down the statement and then I'll explain. Have you written?
yes.
So in this, what I explained to you that we'll be taking a haloalkane that is having beta hydrogen atom, and when you heat this in the presence of alcoholic solution of potassium hydroxide, elimination will take place and hydrogen atom will get removed from beta carbon. That's why this reaction is called as beta elimination reaction. You should remember this. And halogen atom is eliminated from alpha carbon atom and the product is alkene. Now suppose you have some haloalkanes which have forming more than one alkene. So if there's a possibility of formation of more than one alkene, so we apply this rule. Okay.
Okay. Okay, ma'am.
So this rule states that in dehydrohalogenation reaction, dehydrohalogenation means D means removal, hydro is related to hydrogen and halogen is related to halogen only. So in this dehydrohalogenation reaction, hydrogen will be removed and halogen will be removed, and that is happening in this reaction, right? Hydrogen and halogen both are getting eliminated. That's why the name is dehydrohalogenation. Understood?
Yes, ma'am.
So the major product will be that alkene which is having greater number of alkyl groups attached to the doubly bonded carbon atoms. So if I give you one example, that we have 2-bromopentane. So what will be the structure of 2-bromopentane? There will be 5 carbon atoms, right?
Yes,
And
ma'am.
bromine is attached to second position.
Second position. Okay.
So this will be CH3, this is CH2, this is CH2, this is CH3. Fine.
Yes, ma'am.
So the carbon to which halogen is attached, this carbon to which halogen is attached, that is called as alpha carbon, right?
Yes.
And the carbon next to these alpha carbon, they are called as the beta carbons. So can we say that in this example we have 2 beta carbons? Yes or
Yes.
no?
Yes.
Because the carbon atom next to alpha carbon is beta carbon. So there are 2 atoms next to alpha carbon. So there are 2 beta carbons. Fine. And you know
Okay.
that hydrogen atom is removed from the beta carbons, right?
Yes, ma'am.
So there's a possibility that 2 hydrogens can be removed. So one product can be this one if this hydrogen gets removed, and the other product can be this one if this hydrogen gets removed, right?
Yes, ma'am.
So we have this haloalkane that is 2-bromopentane. And now we are heating it in the presence of alcoholic solution of potassium hydroxide. So we are heating it. So we can get 2 products because there are 2 beta carbons. Fine. So this will be product 1 and this will be product 2. And you are heating it with alcoholic potash, that is potassium hydroxide. Okay. So now elimination will take place. So I told you that from alpha carbon atom, halogen will get eliminated, and from beta, one hydrogen will get eliminated, right?
Yes, ma'am.
So when this hydrogen and bromine will get eliminated, there will be a double bond between this, right?
Yes.
So we'll get the product CH3, CH2, CH double bond CH, because one hydrogen will be removed from here and one bromine will be removed from here. So we'll get CH double bond CH and CH3. Yes or no?
Yes, ma'am.
Now, if I remove the hydrogen atom from the second carbon, second beta carbon, so we'll get the product CH3, CH2, CH2, CH. Now from this carbon, we'll remove bromine, and from this carbon, we'll remove one hydrogen. So now we'll get CH double bond CH. Have you understood this?
Yes, yes.
So we can see that in such type of examples, more than one alkene is forming. Now we have to decide which one will be the major product. So for deciding the major product, we have to remember this rule. So what was the rule saying? That the alkene which is having greater number of alkyl groups around doubly bonded carbon atoms. So now first you should see doubly bonded carbon atoms. So these are the doubly bonded carbon atoms, right?
Yes, ma'am.
So around this only one alkyl group is present, and around this one alkyl group is this and one alkyl group is this. So there are two alkyl groups around the first product, right?
Yes.
And there is only one alkyl group around the second one. So which one will be more stable, more preferred? This one, because it has greater number of alkyl groups around the doubly bonded carbon atoms.
Yes.
Yes or no?
Yes, ma'am.
So this will be a major product. So this elimination reaction is quite important. So just go through the examples once again.
Okay.
Done?
Yes, ma'am.
Okay, now I'm giving you one question. Like you have CH3, CH2, CH2, Br. So this is your alkyl halide. This
Okay.
carbon is alpha. This carbon is your beta. So you are having beta hydrogen atom. That means it can show elimination reaction, right?
Yes.
So this compound is heated in the presence of alcoholic KOH. Alcoholic KOH is the reagent for elimination reaction. So it will form a product A, and then it will be treated or reacted with HBr. Do you remember the reaction of HBr? Markovnikov rule, anti-Markovnikov rule?
Yes, 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 I remember.
Okay. So it will form product B. Fine. Now you have to find out the structure of A and B. Now try this question. Have you done
I just got the A1.
A1? First
Yes.
one.
Yeah, the first one.
And what about the second one?
I'm doing it.
Once you are done then. Done?
Yeah.
So can you tell me the name of the compound you got?
Just 1 minute.
Yes, Rufia. Why
Yes,
are you
just 1
taking
minute.
so long?
Okay. A1 I got CH3, CH, and then double bond CH2. It's an alkene.
Yes. Because I told you just now that whenever we heat haloalkane with alcoholic potassium hydroxide, we'll get alkene. So from here, you'll remove this bromine atom, and from beta carbon, you'll
Yes.
remove hydrogen, right? Now,
Yes.
this is the reaction with HBr. So which rule will you follow in the next step?
That one I am doing it.
Do you remember Markovnikov rule?
Yes.
Whenever you are reacting alkene with hydrogen halide, I'll just revise once again. You haven't revised the notes, I think so. Right? You don't revise. Tell me honestly, do you revise or not?
I did.
You did?
Just 1 minute. Just 1 minute.
Okay, so we have alkene and we have hydrogen halide. Hydrogen halides include HF, HCl, HBr, HI, any hydrogen halide, right? So whenever we have alkene and hydrogen halide, we follow Markovnikov's rule. And so you can remember this. Alkene on reaction with HCl, HBr, and HI forms alkyl halide.
Alkyl halide.
And here you'll follow Markovnikov rule. So negative part of the reagent will go to that carbon of the to that doubly bonded carbon which is having lesser hydrogen, right?
Yes.
So in this example, you have HBr. So the negative part is Br minus. So that will go to that carbon atom which is having lesser number of hydrogen. Now tell me the product.
Okay, just 1 minute. Just 1 minute. I'll do it.
Okay. Yes, tell me. Done?
Yes. It's it's CH3 CH with bromine attached to C and then CH3.
Understood? So the
Yes.
negative part will go to that carbon atom which is having lesser number of hydrogen. Well, do you remember this now?
Yes, I will.
So I'm just giving one more question so that I can see whether you have understood or not. This
Okay.
question has come in NEET examination. So previous year. Okay, tell me what's your aim? What do you want to become?
Yes.
What is your aim in your life? What do you wish to become?
Well, I'm going for either IT, engineering, computer science, Bachelor of Computer Science, or Bachelor of Architect.
Okay. So now you have this compound CH3, CH3, and then sorry. So it is CH3, CH3, CH double bond CH2. And you have to react it with HBr.
Okay.
So it is CH double bond CH2 and the reaction is with HBr. So here you have an alkene, right? And you
Yes.
have the reaction with HBr. So which rule will be followed here? I just now told you that whenever
Yes.
an alkene reacts with hydrogen halide, HBr, HCl, HI, then Markovnikov rule is followed.
Yes.
So
Yes.
negative part will go to that carbon atom having lesser hydrogen. So in this question, Br minus will go to which carbon atom? This one or this one? One or two?
One.
One, fine. So if you talk about the mechanism of this reaction, so first H plus gets attacked on this. So if first we attack H plus, so we'll get CH3, CH3. Now in this, on this carbon atom, negative part will attach. That means here we'll have positive charge, right?
Yes.
And here H plus will attack, so we'll get CH3, right? So this is a carbocation. Now tell me whether it is primary, secondary, or tertiary.
Okay, wait. It's tertiary.
Okay, fine. Tertiary or secondary? See this carbon atom. The carbon atom having positive charge. It is attached further to two carbon atoms, right?
Yes.
So it is secondary carbocation.
Okay. Okay.
It is secondary carbocation. Now, if you shift this positive charge here by a hydride shift, right? If we do hydride shift, have you studied about hydride shift?
Wait.
Hydride is H minus. Now see, from this carbon, if we transfer H minus, that is hydride, to this carbon atom, so it will gain a positive charge. This carbon atom will gain a positive charge, CH3, and it has given its hydride. So it will be positively charged now. And H minus is attacking here to CH plus. So it will become CH2, CH3. Yes or no?
Yes, ma'am.
So a hydride shift is taking place. And now can you observe that the carbocation formed, the carbon is further attached to three carbon atoms. So it is a tertiary carbocation, right?
Yes.
And which one is more stable, secondary or tertiary?
Tertiary.
So this will form the product. So now the Br minus, it will attack here to this carbon. And your product will be CH3, CBr,
CH3, CH2,
CH3.
CH3.
Understood?
Yes, ma'am.
So this is called as rearrangement. Whenever there is a possibility of forming a more stable carbocation, we rearrange the compound to form a greater stability carbocation. Fine?
Yes, ma'am.
So this example is important. Now the second type of reaction is completed. Now the third one. So third is reaction with metals. reaction with metals. Okay, first tell me what are organometallic compounds.
Wait, I know this. I know this. Wait, it's a chemical compound uh, which contains at least one bond between metallic element and carbon atom.
Yes.
Okay.
So it is a compound having metal carbon bond. So in this we have the reactions that you have taken an alkyl halide Rx, fine, because alkyl groups they are represented by R. Yes or no?
Yes.
And you are reacting it with magnesium, a metal, and in the presence of dry ether. So it will form RMgX. Okay. You know
Okay.
that halogen atoms are electronegative. So it will have negative charge and this will have positive charge, right?
Positive. Yes.
If this is having positive charge, so this will have negative charge. Okay.
Yes.
And now tell me what is the name of this compound? RMgX.
RMgX.
It is a general form of a compound. Grignard reagent. Remember?
Yes, yes.
So whenever alkyl halides react with magnesium in the presence of dry ether, they form Grignard reagent. So if we have taken the example CH3, CH2, and Br along with magnesium in the presence of dry ether, can you tell me the product?
Okay. With Br, right? CH3, CH2, Br.
Br, yes. Observe the first reaction. Rx plus Mg is forming RMgX. So in this example, your R is CH3, CH2, right?
Yes.
So first write down the alkyl group part, then you have to write Mg and then you have to write X. And X is bromine here. So you'll write MgBr. That's it. So the product is CH3, CH2, MgBr. Now, if I ask you the general name of this Grignard reagent, so you know that R stands for alkyl, right?
Alkyl, yes.
And then we have magnesium.
Magnesium halide.
Yes, so it is called as alkyl magnesium halide. So you should remember this. And now you have to remember that Grignard reagents, they are very reactive. This RMgX, Grignard reagents, they are very reactive and they react with any source of proton. If they are seeing any compound with H plus, with a proton, they'll react with it and form hydrocarbon. So you should remember that RMGS, Grignard reagents, they are very reactive and they'll react with any source of proton to form hydrocarbons. So suppose we are having RMGX, Grignard reagent, and we have water. And you know that water is H plus and OH minus, right?
Yes.
So proton is present in water. So what will it do? R minus. I told you that R has negative charge. So R minus will combine with H plus and it will form RH. So RH is your hydrocarbon.
Hydrocarbon.
And along with it Mg, and from H2O, OH, OH will be left and X. So here it will be formed. So that's why we have to perform the reactions of Grignard reagent in dry conditions. That's why we are using dry ether here. We should avoid it from moisture because if it combines with a source of proton, it will form hydrocarbons. Okay, so the reaction is carried out in dry ether and we have to avoid even small amount of moisture from a Grignard reagent. And this reaction can be used as a method for forming hydrocarbons from Grignard reagent, right?
Yes.
Now the next reaction is Wood's reaction. Do you remember this?
Wait.
Wood's reaction.
Yes, I remember this.
Tell me. Okay, I'll tell you.
Wait,
We
you
have-
want me to tell you? It's a coupling reaction wherein sodium metal is reacted with two alkyl halides.
Yes. So we have Rx, we have sodium, and then we have another molecule of alkyl halide. And they react in the presence of dry ether. Right? So alkyl halides react with sodium and dry ether and they form hydrocarbons. So what will happen in this reaction? That this Na and this X of these two alkyl halides, they combine to form two NaX, and along with this R and this R will join. So we'll get alkanes, we'll get hydrocarbons and two molecules of NaX.
NX, okay.
So if I say that the alkyl halide is having only 2 carbon atoms, so this alkane will be having 4 carbon atoms, right?
Yes.
That means that carbon atoms, number of carbon atoms is getting doubled in the hydrocarbon. If here it is having 2 carbon atoms, so it now the total number will be 4 carbon atoms. So the number of carbon atoms is getting doubled. Is it clear?
Yes, ma'am.
Okay. So these were the 3 reactions of haloalkanes, that is alkyl halides. First was nucleophilic substitution, SN1 and SN2. Second is elimination reaction in the presence of alcoholic potassium hydroxide, and third is reaction with metals. So this you should remember, Wood's reaction. Name reactions are always important. Thank you.
Yes, ma'am.
Now next we'll discuss about reactions of haloarenes. What are haloarenes?
Wait. It's same as haloalkanes but with benzene ring.
Yes. So the other name of haloarenes is aryl halides. That means halogen atom is directly attached to the benzene ring. Fine.
Okay.
So here also it shows reactions. First is nucleophilic substitution, then electrophilic substitution, and third one is reaction with metals. So first one we'll discuss nucleophilic substitution reaction. So what happens in nucleophilic substitution?
Oh, wait. Okay, you're doing from the starting.
No, I'm doing it for haloarenes. Till now, we were doing it
Okay.
for haloalkanes that were having different type of reaction, but 2 were common. The 3 reactions showed by haloalkanes are nucleophilic substitution reaction, second one was elimination reaction, and third is reaction with metals, right? Now we are starting with the reactions of haloarenes, that is aryl halides, in which halogen atom is directly bonded to the benzene ring.
Okay.
So now I'm just asking you simply that what is nucleophilic substitution reaction? How much do you remember? That's what I'm checking.
Oh, okay.
Now tell me what is nucleophilic substitution reaction? You told me that you have revised the chapter. How much I have
Yes.
forgotten. So tell me.
Okay. It's the reaction. Wait. It's a reaction in which an electron-rich nucleophile attacks a positively charged electrophile to replace a leaving group.
So it means that we have an existing nucleophile and that is replaced by a new nucleophile, right?
Yes.
So fine. So it is said that aryl halides are less reactive towards nucleophilic substitution. Aryl halides or haloarenes, they are extremely less reactive. This you should remember, that they are very less reactive towards SN reaction. That means nucleophilic substitution reaction, towards SN reaction. Now there are two reasons behind this, that why they are extremely less reactive. So the first reason is, like I'm taking the general example of aryl halide. So if I have taken chlorobenzene, chlorobenzene is chlorine attached to benzene ring, right?
Benzene ring. Yes.
So we have this, and you know that halogens have 3 pair of lone pairs on them, right?
Yes.
So this is chlorobenzene, and now there's a tendency that this lone pair is going there. It is involving in conjugation with the ring, benzene ring, right? Resonance is
Yes.
there. So these lone pair will shift here. This bond will shift here. Right? So what will be the next? So we are drawing resonating structures, and you know that resonating structures are separated by a double-headed arrow, right?
Yes,
So
ma'am.
if chlorine has shared its electrons to the ring, now chlorine will gain a positive charge, right? Because it has donated its electrons. And 2 pairs of lone pairs are still present. And now on this carbon atom, negative charge will be present, right?
Yes, ma'am.
So again, this negative charge can delocalize in the ring. And this double bond can shift here. So we'll get the next structure. Here negative charge will come. Here will be double bond, and the bond is same, Cl plus. Now again, this negative charge can shift here, right? And this bond can shift here.
Okay.
So here it will be negative charge, and now we are having double bond, right?
Yes, ma'am.
Then this negative charge can shift here, and this bond can go back to chlorine. Bond is simply electrons. So here delocalization of electrons is taking place. So now double bond has come here, here, and here. And we have now got back the 3 lone pairs. Fine. Have you understood
Yes.
this?
Yes.
So how many resonating structures are there? 5.
5.
Now can you see that this negative charge is coming on which positions? Ortho, meta, para, which positions?
It's in para position, right?
It is also there in ortho position.
Yes.
1, 2 position is ortho. So this one is ortho with
Ortho
respect to
position.
chlorine. This one is para with respect to chlorine, and this one is ortho with respect to chlorine. So you should remember that negative charge is present on ortho and para positions.
Okay.
This is important. And 5 resonating structures are there. And now observe the bond between carbon and chlorine. Now, can we say that it is having partial double bond character? Because in some of the resonating structures, there is a double bond between carbon and chlorine. Yes or no?
Yes, ma'am.
So the CCl bond is having partial double bond character,
Character. Okay.
right? Because of resonance. So can we say that this bond is difficult to break now because it's having double bond character? Yes or no?
Yes, ma'am.
This carbon and chlorine bond will be difficult to break. That's
Yes.
why this is one of the reasons why these aryl halides, haloarenes, they are less reactive. Understood?
Yes. Okay.
Because the lone pairs on the halogens, they were involved in the conjugation, in the resonance with the benzene ring. And then we got 5 resonating structures, and we observed that the carbon and halogen bond, or the carbon and chlorine bond in this example, it is having a partial double bond character, due to which the breaking of bond becomes difficult, right? So this is one of the
Yes.
reasons why it is less reactive. And you should remember that the negative charge is coming only on ortho and para position, right?
Okay, ma'am.
Okay, so the next reason is difference of hybridization. Now, if we talk about alkyl halide, so alkyl halide is simply Rx. So it is having, suppose the example is CH3X. Now tell me, what is the hybridization of carbon? I told you in the beginning of this chapter.
Hybridization of the carbon.
In alkyl halide, yes.
Wait. It's sp2 minus.
No.
It's sp3.
Yes, because it is having 4 sigma bonds,
Or
right?
yes, ma'am.
So the hybridization of this carbon is sp3. And if we talk about aryl halide or haloarine, you can observe that the halogen is directly attached to this carbon atom, right? Benzene ring. Now tell me the hybridization of this carbon.
Okay, it's sp.
It is sp2 because it is forming 3 single bonds. 1, 2, 3.
Okay.
Remember that if it is forming, if Z is equal to 2, that means it is sp. Z is hybridization. If Z is
Okay.
equal to 3, it is sp2. And if Z is equal to 4, it is sp3.
3.
Fine. So
Yes,
here
ma'am.
it is forming 3 single bonds. That's why it is sp2. If it is forming 4 single bonds, it is sp3. Remember like this, right?
Yes, ma'am.
So you can observe, and this you should remember that in alkyl halide, the carbon is sp3 hybridized, whereas in aryl halide, it is sp2 hybridized. Now, if we talk about the electronegativity of these carbons, now tell me, what is the order of electronegativity? sp hybridized carbon, or sp2 hybridized carbon, or sp3 hybridized carbon? The order of electronegativity. You must have studied this.
Yes. It's first sp and then sp2 and then sp3.
Which one is the most electronegative?
It's sp.
Yes. And the reason is because of the percentage of S character.
Yes.
So what is the percentage of S character in sp? See, there are 2 parts. So 100 divided by 2 is 50%. That means S is having 50% character. In
Yes.
sp2, we have 3 parts. So 100 divided by 3 is 33.33. So this is the percentage S character in this.
Okay.
And in this, we have 4 parts. So 100 divided by 4 is 25%. This you should
25%.
remember. And you
Okay.
should remember that electronegativity is directly proportional to the percentage of S character.
sp. Okay, S character.
That's why greater the percentage of S character, greater is the electronegativity. So sp is more electronegative than sp2 and then sp3. Okay.
Okay, ma'am.
So listen it once again. In haloalkanes, the carbon to which halogen is attached, that is sp3 hybridized. This carbon to which halogen is attached, this is sp3 hybridized. Whereas in haloarenes, the carbon to which halogen is attached, that is sp2 hybridized. Okay?
Okay, ma'am.
First one. Now, then you should remember that electronegativity is directly proportional to S character. So greater the S character, more is the electronegativity.
Electronegativity. Okay.
Now we have sp2 hybridized carbon and we have sp3 hybridized carbon. So which one is more electronegative? sp2, right?
sp2, yes.
So the one having greater S character will be more electronegative
More
and will
electronegative.
hold the electron pairs more tightly, more strongly. So in haloalkanes, in aryl halides, it is sp2 hybridized. So it will
Yes.
hold the electron pairs more tightly. So the bond breaking will be less difficult, more difficult, right?
Yes.
Because the bond is tighter. It is stronger. The electrons are held tightly. So the loss of electrons won't take place so easily. So bond cleavage will be difficult. It will be difficult to break the bond. So this is the second reason why haloarenes are less reactive.
Yes.
Understood?
Yes. Yes.
So this you should remember. Then you should remember some reactions. So suppose we have chlorobenzene. Benzene and chlorine is there. And if you react it with NaOH at 623 Kelvin and 300 atm pressure, that means you are taking very high pressure and temperature conditions. So this chlorobenzene will get converted into phenol. This you have to remember. And phenol is benzene ring attached with OH. So chlorobenzene can be converted into phenol by reacting it with sodium hydroxide solution at a temperature of 623 Kelvin and 300 atm pressures. And then you have to react it with H+. So there are two steps. First reaction with NaOH at this temperature and pressure, and then is acidification. Reaction with H+, so it will form phenol.
Okay.
Now you can see that it is needing very high temperature and pressure conditions, right?
Yes.
So if we introduce an electron withdrawing group is NO2. An example is NO2. So what it will do, it will withdraw the electron density from the ring.
Yes.
It will make it more electron deficient. And now you are reacting it with NaOH. Now the reactivity of the benzene ring has been increased, haloarene has been increased. So it would require lesser temperature. Now the temperature is 443 Kelvin and H+. So the Cl will be replaced by OH and NO2 is still present. So here we have NO2 at para positions. We don't have it at ortho. Now, if we have introduced this NO2 group at both ortho and para, now the activity will increase more because two electron withdrawing groups are present, right?
Yes, ma'am.
So now it would need a lesser temperature, like 368 Kelvin. So you can see the temperature is decreasing. And now the Cl will get converted into OH and NO2 will remain as it is. Now, if we have attached NO2 groups at all the ortho and para positions, so we are having chlorobenzenes and NO2 is present at all ortho and para. So all the positions are occupied, then it is very reactive. Now it will just need warm water, warm conditions, and it will form this. Cl will be replaced by NO2.
N.
So by increasing the number of electron withdrawing groups at ortho and para positions, the reactivity is getting increased, right? Can you observe?
Yes, ma'am. Okay.
So this was about nucleophilic reactions, nucleophilic substitution reactions. Now the second type of reactions of haloarenes is electrophilic substitution reaction. Just electrophilic substitution. So earlier it was nucleophilic substitution in which nucleophile was attacking. Now here it is electrophilic, that means electrophile will approach the benzene ring. So it is electrophilic substitution reaction. Do you remember how many types of electrophilic substitution reactions are there? Okay, I'll tell you. Electrophile are electron deficient species, right?
Yes, ma'am.
So electrophile can be represented like this. And they want to attack positions which are electron rich, right?
Yes.
Because positive charge attracts negative. So electron deficient species will attack the regions which are electron rich. So benzene ring, you know that benzene ring is electron rich because it is having pi bonds and which are getting completely delocalized in the rings, right? Yes or no?
Yes, ma'am.
And just now we have drawn the resonating structures of chlorobenzene. So you can see here that because of resonance, the electron density was increasing at ortho and para positions, right?
Yes, yes.
So electrophile has a tendency to attack at these positions because these positions are rich in electrons, right?
Yes.
So whenever the substitution will take place, it will take place at ortho and para position because there the electron density is high. So we can say that halogens are ortho para directing groups.
Yes, ma'am.
Ortho para directing. Do you know ortho para directing groups?
Yes.
Which
Ortho.
send the group to ortho and para positions, right?
Yes.
So first type of electrophilic substitution is halogenation. Remember?
Yes, halogenation. Yes, 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 I remember.
So we'll be having a chlorobenzene and we are performing halogenation reaction. That means we'll react it with halogen molecules. So suppose we have taken chlorine. And then this reaction takes place in the presence of a Lewis acid, and that is anhydrous AlCl3. And you should remember the electrophile generated in this reaction is Cl+, which is called as chloronium ion. So electrophile will approach this benzene ring, which is electron rich, and you'll observe that the Cl will get attached one time to the ortho position and the other time to para position. So two products are formed. One is 1,2 dichlorobenzene, right?
Yes.
And what is the name of the other compound?
It's 1
4. This is 1,
4
this is 2,
and 4.
3, 4. Yes. So it is 1,4 dichlorobenzene.
Chlorobenzene.
Now tell me which one will be the major product.
Okay.
See here, both the groups are very close to each other. So here will be
Yes.
repulsion, so it will be less stable. And here
So
the groups
okay,
are
so
very
it's
far away.
1,4 dichlorobenzene.
So this will be your major product and this will be your minor.
Minor.
This way you have to identify the major and minor products. So, and you can observe that these groups are introduced to ortho and para positions, right?
Yes.
That's why halogen atom was called as ortho and para directing group. Next is your nitration. So for nitration, we'll react chlorobenzene with concentrated HNO3, nitric acid, and concentrated sulfuric acid, H2SO4. And here the electrophile is NO2 plus nitronium ion. So one time NO2 plus will get attached to ortho position and on the other hand it will get attached to para position.
Para position.
So we'll get the sulfur product of this. Understood?
Yes, ma'am.
Okay, now tell me the names of these two compounds.
Okay. 1,2.
No, it won't be 1,2. It will
No.
be 1-chloro, 2-nitro-benzene. Right?
Okay. Yes.
Tell me the name of the other one.
Um.
See, chlorine is present on the first position and nitro is present on the fourth position. And if we observe alphabetically, chloro is kept coming first, right? Because
First,
C
yes.
comes first. So that's why the name is 1-chloro, 2-nitro-benzene.
Okay, so 1-chloro, 4 nitro.
4-nitrobenzene. Yes, correct. So it is 1-chloro, 4-nitrobenzene.
Nitrobenzene.
Because naming always takes place alphabetically, right?
Yes.
Is it clear till now?
Yes, ma'am.
But you have to revise after the class. Okay. Next
Okay.
is sulfonation. So in sulfonation, sulfonic acid group will be introduced. Nitration means introduction of NO2 group. Halogenation means introduction of halogen groups to alpha and para. Sorry, yes, ortho and para positions. In sulfonation, sulfonic acid group will be added. So we have chlorobenzene and we are reacting it with concentrated H2SO4. And we are also heating it. So here sulfonic acid group will be added. That means SO3H will be added one time at ortho and the other time at para. So it is Cl SO3H. Understood?
Yes, ma'am.
Now tell me the name of these two compounds. And you can identify major and minor, right? This one will be minor because the two groups are close to each other. And this one
Yes.
will be major. In the upper one also, para product is major and ortho is minor. This is minor, this is major. Done? Now tell me the names of these two compounds.
Okay. Well, it's sulfonic acid, right?
Yes.
So it's 1-chloro.
No. Now this
Okay,
sulfonic
it's 1,
acid.
2.
No. Just wait. This sulfonic acid will have a greater priority. While studying nomenclature, you must have studied the priority order for naming, right?
Yes.
So this gets greater priority. So this will be 1 now and this will be 2.
Okay, yes. Okay.
So the name will be 2-chloro-benzene sulfonic acid. Understood?
Sulfonic acid. Okay.
And what will be the name of this one?
It will be, okay, wait. It will be 2, no, it will be 4-chloro.
Yes, it will be 4-chloro-benzene sulfonic
Sulfonic
acid.
acid.
Understood?
Yes.
Any doubts?
No, ma'am.
So next one is your Friedel-Crafts reaction. Do you remember Friedel-Crafts?
Wait. Yes.
Alkylation, acylation.
Yes, I remember.
So first we'll study alkylation. In alkylation, alkyl group is introduced to the benzene ring. So we'll have benzene ring, so halobenzene Cl, and we'll react it with alkyl halide. So suppose we have taken CH3Cl.
Yes.
And you are reacting it with anhydrous AlCl3. So now here the electrophile generated will be CH3 plus, whatever is the alkyl group present. So this alkyl group will get introduced into the benzene ring at ortho and para position. So it will form ClCH3 plus ClCH3. Understood?
Yes, ma'am.
Now suppose if instead of CH3, it was C2H5Cl, then C2H5 would have got attached to the benzene ring. Fine. So
Yes,
this is
ma'am.
example of alkylation reaction in which alkyl halide is reacted with haloarine. Now next is acylation reaction. Friedel-Crafts acylation. So you must have seen this type of compound, CH3, C double bond O and Cl. The general form is RC double bond O and Cl. Acetyl chloride, right?
Yes, yes.
So if you react chlorobenzene with acetyl chloride, that is CH3, C double bond O and Cl, in the presence of anhydrous AlCl3. So here the electrophile generated will be CH3, C double bond O and plus charge on this carbon. So it will get attached to the benzene ring through this carbon at ortho and para positions. So here Cl is present. So one time it will be C double bond O CH3, right?
Yes, ma'am.
And the other time it will be at para position. So it will be C double bond O CH3, right? Understood? So when this
Yes.
electrophile attached is this. Every time you should remember which electrophile is getting attached. Okay, now tell me the name of this compound. Do you remember? On benzene ring, COCH3 is present. This is called as acetophenone.
Acetophenone. Okay.
Remember?
Yes, yes. Acetophenone.
Okay. Now you can see that this is on the first position and this is on the second position. So the name can be 2-chloroacetophenone.
Chloroacetone, not benzene.
Not benzene, it is acetophenone.